Okay. Passive high pass filter first. Yeah? Passive high pass filter. So in passive high pass filter, of course, ideally what we want is a circuit that can pass all the signal above certain cutoff frequency. So this is the cutoff, this is the frequency, and this is the amplification. And cut all the signal below that frequency cutoff. Yeah, so this will be the stop band, and above the FC, above the cutoff frequency, will be the pass band. But in reality, it is not like that. So in reality, what we will have is similar to low pass frequency. Yeah, something like this. We will also have a cutoff frequency. Yeah, at cutoff frequency, the value is 0.7071 or 3 decibel compared to the center value of the frequency. Yeah, so this will be 0 dB. Yeah. So above here is amplification. This is frequency. And the cutoff frequency is basically has similar formula as in the low pass frequency. So cutoff frequency equals to 1 over 2 pi RC, or omega C equals to 1 over RC. Yeah, usually the circuit looks like this. So what we have is capacitance first, yeah, and then resistor. Yeah, so the output is in the resistor. This is capacitance, and this is the resistor. This is V input, and this is the V output. Okay, so here, if we have, for example, multiple, we have the low frequency component, we have the middle frequency component, and we have a very high frequency component. If we put into the filter, low pass, high pass filter, yeah, the low component part and medium part will be cancelled. So what we will obtain is only the high frequency component. So it only pass this very high frequency component. So that is how it works. So based on the circuit drawn here, the formula to obtain the V output as a function of the V input can be derived using voltage divider formula. However, now we have to take into account the frequency domain. So using the reactance of the capacitance, yeah, R divided by R plus XC multiplied by the input voltage. Okay. So in high frequency, high pass filter, when omega is 0, yeah, when omega the frequency is 0, then P output will be 0, yeah, like this, like here. So when omega equals to infinity, then we have more or less V output will be equals to V input, the input voltage. Yeah. And when omega equals to the omega C, then V output equals to 0.7071 V input. Okay. Save and yeah, drawing. So let's derive how we get this formula Fc equals to 1 over 2 pi Rc. So from the previous drawn circuit, then the transfer function is R divided by R plus Xc multiplied by Vn, or like this. The magnitude of V out divided by V in will be equal to the magnitude of R divided by R plus XC. Then V out divided by V in, the magnitude equals to R square, yeah, R square, or not R square, sorry, so just R divided by and the square root of R square plus XC square. Okay, so at when frequency equals to the cutoff frequency, hence the P out divided by P in, okay, will be equal to 1 over square root of 2. So this is equals to R divided by square root of R square plus XC square. So when we square both sides, what we will have is 1 over 2 equals to R square divided by R square plus XC square. Okay, then from here we can see that R square equals to XC square. Okay, equals to 1 omega square C square. Then omega square equals to 1 over R square C square, or omega equals to 1 over RC. So here FC equals to 1 over 2 pi RC. And the phase change will be equals to 1 over arctangen of 1 over omega CR. Okay. So again, the output equals to the R divided by R plus XC multiplied by V in, okay, or V out divided by V in equals to R divided by R plus XC, so equals to R divided by R plus 1 over J omega C. So this is also equals to 1 over, so if we multiply this part with J and J divided by J, so we will obtain R minus J divided by omega C. Okay, then we divided, sorry, if we have divided by R, all the sides, then this becomes also 1, and this become 1, and we obtain here R. Okay, so we divided both numerator and denominator with R. So from here we obtain that the phase change due to this high pass filter circuit is negative arctangen of minus 1, because this is in the lower part, okay? Minus 1 arctangen minus 1 over omega CR. Yeah, since this minus can be put into the inside of the terms here, minus multiplied by minus, so this equal to arctangen of 1 over omega CR. So this is the formula for phase change in a high pass filter. So what does it mean is when omega equal to 0, so this is high pass filter, this is the inverse of low pass filter, so it means the phase will be equals to 90 degree, right? Omega equals 0, so this value equals to infinity. Arctangen infinity is 90 degree. When omega equals to omega c, which omega c equals to 1 over RC, so this part inside the terms will be equal to 1. So the phase changes will be equal to 45 degree. Then when omega equals to infinity, so this value equal to 0, arctangen 0 is 0 degree. The phase will be change equal to 0 degree. Yeah, so that is the phase change of a high pass filter. So if we draw the phase change, it is the inverse or the opposite of uh, low pass filter, yeah, or the opposite of low pass filter. So we can draw it something like this. At infinity, it is approaching 0, while at FC, this is 45 degree, and when F equals to 0, the phase change equals to 90 degree. Okay, okay, save this and give some example to be calculated. Yeah, to be calculated. We have here a high pass filter. Okay, high pass filter. This is R and this is C. Let's see if we would like to design a high pass filter with cutoff frequency of 10 kilohertz. Okay, 10 kilohertz. Yeah, and R resistors equals to, let's say, what should be the value of R and C? Okay, so let's say then if we choose the resistor to be 10 kilo ohm. Yeah. Why 10 kilo ohm? Because if we put too small resistor, for example, uh, below 100 ohm, for example, then much current will be drawn through here, okay, to this, and then it will create loading to the next circuit. But if we put too high resistor, also 1 mega ohm, for example, the capacitance will become too small. If capacitance becomes too small, then there will be parasitic capacitance also occurring in this circuit, which also we don't want that. So what will be the value? So from the formula, the Fc equals to 1 over 2 pi Rc. And here we design the cutoff frequency to be 10 kilohertz. So if we put into the calculation, equals 10 kilohertz equal to 1 over 2 pi 10 kilohertz, 10 kilo ohm, or 10 to the power of 4, yeah, ohm multiplied by the C, yeah, multiplied by capacitance. So here we obtain C to be equal to 1.59 nanofarad. Okay, but in the market, in the component list, you cannot find 1.59 nanofarad. What you could find closest to this is C equals to 1.5 nanofarad. So then let's put again to the formula. If we calculate this, yeah, calculate this. Anyone can have calculator. So Fc equals to 1 over 2 pi 10 to the power of 4, 1.5 times 10 to the power of minus 9. What will be the value of Fc? Let's see. Anyone has calculator?
10,000.
Huh?
10,610.
10,000?
610.
600 hertz, yeah? Okay. 1,600. See, then we have about, so the cutoff frequency is shifted towards a bit higher frequency. So if we would like to push it towards towards closer towards 10 kilohertz, what we can do is we want to make this value smaller. what we can do is the C we already fixed to 1.5 nanofarad. What we can do is we try to increase the value of the resistance. So then let's try to use, instead of 10 kilo ohm, let's pick the R to be 20 kilo ohm. So just twice the value of this. So then a new FC will be 1 over 2 pi, 2 times 10 to the power of 4, 1.5 times 10 to the power of minus 1. What will be the new value of the cutoff frequency? Anyone? That's the calculator. With the new resistor value, 20 kilo ohm. Anyone can calculate, please? Nasser, Risto?
5,305.
Huh?
5,305.
Oh, become 5,000, yeah? Okay. 5,305, yeah. So here now the value hertz, yeah? So it is much less, yeah? So what we can do then is instead, we will put a potentiometer, something like this. Yeah, let's say this is 20 kilo ohm. So instead of fixed resistor, what we can do is to have a potentiometer there. So we can vary the value between 20 kilo ohm and 10 kilo ohm. Yeah, and to reach an FC of 10 kilohertz. So maybe it's not, maybe the value is not fixed 20 kilo ohm or 10 kilo ohm, maybe around 11 kilo ohm, 12 kilo ohm, something like that. Yeah, but that value is usually difficult, right, to find exact 12 kilo ohm, something. Usually you could also combine 10 kilo ohm with 2 kilo ohm, but the tolerances in each of the resistors may cause the circuit not accurate, yeah, not precise. Then what you could do is by putting a potentiometer like this instead. Okay, so from here then what we will have will be something like this. A high pass filter with cutoff frequency 10 kilohertz. Yeah, if for example V in is 10 volt, let's assume that V in is 10 volt. So at around 10 kilohertz, the value will be 7.07 volt. Yeah, so this is minus 20, an increase of 20 decibel per decade. So at 1 kilohertz, the value will be 0.707 volt, something like that. Yeah? So this is the frequency. So what then if we want the value, yeah, of the high pass filter to become sharper, yeah, to become sharper. So instead of like this, we want to have, for example, sharper like this. So then the cutoff frequency is closer to the actual 10 kilohertz, for example, or even sharper like that, for example. So then this can be done if you put multiple high pass filter to make a higher order high pass filter. Similar can also be said for low pass filter. If you combine several low pass filter, then you can use, you can make a higher order uh, low pass filter, yeah, to develop a sharper filter, either low pass or high pass filter. So, for example, yeah. So what you can do is you, for example, in this case of high pass filter, yeah, you can develop two loads of cascaded uh, high pass filter. C1, C2. This one is R1 and R2. Here the cutoff frequency will be equal to 1 over 2 pi square root of R1 C1 R2 C2. If you pick the component C1 to be equal to C2 and R1 to be equals to R2, then this becomes Fc equals to 1 over 2 pi R1 C1, if it is the same. The disadvantage, however, when you combine such circuit is then the voltage output may decrease from the voltage input, because of the loading effect. So what you can do is then instead you put a buffer on it. A buffer, remember, voltage follower that we have discussed last week, I believe, last week in the circuit. So you don't put directly the circuit into the next RC circuit, but instead you put into a voltage follower circuit using op-amp, for example. So then this is what we call as active high pass filter or low pass filter, if the C and R is reversed. Active high pass filter. Okay, that's all for this second hour. Later in the next hour, we will have a bit of exercise, for designing high pass filter, for the other student which do not yet have done. Okay, with that, don't forget to fill in your attendance. Let me look again.